Welcome to Chapter 23. This chapter is all about Gauss's Law, which is a summary of all of electric fields and electric forces and how they work together. And it's going to involve flux and dot products and all these things, so it can be pretty complicated and intimidating, but it is simply stunning in its beauty. When Einstein first saw Maxwell's equations, and this is one of Maxwell's equations, by the way, he said that they were one of the most beautiful things that he had ever seen. And so it can be intimidating, but I hope that we'll understand it. We'll walk through this together, and it'll all be good. So here we go. So things to keep in mind, again, electric field lines, they follow the same direction as the field vector at any point on a positive test charge in a region of space. Flux. Flux is often the rate of flow through an area, right? But it also can be seen as the dot product of the area vector with the field going through that area at any time. Okay, so electric flux is the rate of flow of an electric field through some given area. Okay, and it's represented, you can think of it as the number of electric field lines that go through that area. And so we're talking here about a surface area vector, and that can be confusing. How do we have an area vector? So an area vector, on to the next slide, the magnitude of an area vector is just the area. You calculate the area, the surface area of that thing. The direction of the area vector is perpendicular to the surface at that point. Right. And so here's an example. This is what you see here on your page. Here's side E, A, B, C, and D. If we're kind of holding it up like this, right? So if this is positive X, let's see, this would be X, B, so X, Y, Z, we have, does that work? X, Y, or wait a minute, let's do X, Y, and Z, so B, yeah, okay, so that works. So then if we hold it like this, that's the positive X, this is Y going out that way, nope, rather, Y is this way, and Z is coming out that way, so we're looking at side B, like in that side view. So the area vector of side A, which is this, would be 9, negative I. Okay, and then for B, this is coming out, right, perpendicular to the surface, would be out into the screen, like to you guys. So that would be 6 meters squared, positive K hat, right, that's the Z direction. As for side C, that's this side over here, so that's like coming out this way. That would also be 6 meters squared, calculate the area. All right, 1/2, 4 times 3, 1/2 base times height, because it's a triangle. And then in the negative K, D is this side down, so that's negative J, and it's 12 meters squared, negative J. And then this piece here, this is at some angle. You can see it's a 3, 4, 5 right triangle. So we can think of our vectors, the sides of this, when we do the angles, we could just do things in terms of fractions, right? Sine, cosine, that kind of thing. So let's take a look at that one. All right. So it looks like this. Area vector A is 9 meters squared, negative I hat. Area vector for B was 6 meters squared at positive K hat. C was 6 meters squared, negative K hat. A, D, 12 meters squared, negative J hat. And then if we look at the area vector for side E, that's going to be, it's like 15 meters squared, but realize that it's at an angle as well. So it ends up being this 15 times 3/5 I hat plus 15 times 4/5 J hat. All right. So then what is the total area of the enclosed surface? If I add all of these up as vectors, you know, 6, -6, +6, those cancel out, so k direction is all 0. You know, 15 times 3/5, well, that's 9. So this I and this I cancel out, and then this j and this j cancel out as well. So the total area vector is 0. Right? And that's going to be true for any enclosed surface. Okay, so now looking at electric flux now through this whole thing. If I take this and I imagine that I have an electric field going vertically downward, right? Then I can take the dot product of the field and the area vector for any of these. Now, if I have this field coming down like this vector field points that way. The dot product of two vectors that are 90 degrees, you know, this way and this way, is just 0. So for B, A, and C, the flux is going to be 0. And you think about this, if this is going straight down, there are no electric field lines going through these sides. Okay. So phi A. Phi is what we use for flux. It's a capital phi, if that makes a difference to you. That's going to be 0. Phi of B is 0, and phi of C is 0. Phi of D then is E dot A. So that's going to be, it's 200 newtons per coulomb is the electric field, it says there at the top of the page. And the area vector is 12 meters squared. Right. And the angle between these two is 0, right? This vector is pointing straight down, and the field vector is pointing straight down. So they're both parallel to each other. So cosine of 0. And we end up here with 2,400 Newton meters squared per coulomb. Okay, and then what about phi of E? So that again is E dot A. So again, 200 newtons per coulomb times, this one is 15 meters squared. But again, it's, and then the angle there is the 4/5. Okay, and so this also gives us 2,400 Newton meters squared per coulomb. And this flux is going, you know, down out of this side, and this one's coming in from the top. So then when we add them up, because this one's negative, this one will be negative. When we add them up, the overall net flux is 0. All right, so phi net equals 0. And that's a general rule, that the net electric flux through any closed surface that surrounds no charge, as long as there's no charge in here, always the net flux will be 0. And so we can see in this, if we have no charge inside of a box, there is 0 flux. If there is 0 net charge, then the inward flux and the outward flux cancels out. And here, if there's no charge inside the box, then the inward flux cancels out the outward flux as well. So as long as the net charge inside of a closed surface is 0, then the net flux is going to be 0. Okay. You know, these two really are the same. They both have positive Q. That means you have the same number of field lines that are coming out. This one, you have twice as many field lines coming out. Notice here that it only depends on the amount of charge inside the closed surface, no matter how big that closed surface is. Right. Here, you've got all these field lines going through here, so the flux is just E times A, right? They're parallel. Here, this is going to be E A cosine of phi, right? Because it's at an angle here, so that's affecting the flux. Here there is zero flux, zero field lines going through this one, and they are perpendicular. The area vector is perpendicular to the electric field lines, right? And we're going to be dealing with things typically in terms of theta, so you can change all these to thetas if you want. It might be less confusing because capital phi is the flux itself. Okay, Gaussian surfaces. As you can see, the shapes, it could be any shape really, the way it works out, but we're going to deal with shapes that are easy to deal with. Ones with known geometries where we can find areas and things like that pretty easily. And so a Gaussian surface, again, is a hypothetical or imaginary closed surface. It has to be closed, that's important. And we're going to use usually spheres, cylinders, pillboxes, and we're going to pick one of these depending on what's convenient for the problem. And again, this Gaussian surface is a mathematical construct. It does not have any real surface. We're just using it to help us calculate flux. All right? And for a spherical Gaussian surface, the surface area of a sphere is 4 pi r squared. Now that should look familiar from the fact that k is equal to 1 over 4 pi, there's the 4 pi, epsilon naught. All right, so let's keep moving and we'll see where that plays in later. All right, so again, it could be any closed surface. The ones we're going to use are going to be known geometries, but it could even be something weird shaped like this. But a sheet of paper, a loop, anything that's open is not a Gaussian surface. Okay, and then we can think about flux in terms of counting field lines. Because we care about just the net flux, right? Any line that goes in and then comes out again counts as 0. So when we're counting the field lines, we can do a +1 for everything that comes out, a -1 for everything that comes in, right? Lines going in means negative, lines going away from something means positive charge. And so if we have a +2 and a -2 charge, here, how many lines are there around this Gaussian surface, or coming out of this? We count there are 8 lines coming out. You can count them 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, right? Not 9. 8. So this would be +8. Right? What about this? Again, it's just surrounding this one charge. So how many lines are going out? Well, if you count 1, 2, but negative, 3, but -1, but +1, eventually it just comes out to 8 again, right? You can count, this is plus, minus, plus, 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 add them all up, and again you get +8. Same thing, right? Here you got these lines coming in, there are 8 lines going in, so you get -8, but even a weird shape, right, it just encloses this one. All these lines, if you count the number of times they go in and then out again and then back in, eventually it adds up just to -8, right? But what about this? There's no enclosed charge. That means every line goes in and then out. Some go in and out again. And so here you have net 0, just counting up those field lines. What about inside here? 0. There is 0 net charge inside. Therefore, there are 0 net field lines passing through the Gaussian surface. Okay. So what do we know about what's inside this box? If these represent electric field lines, we know that there is a net positive charge inside that box. Okay. And so here is Gauss's law, basically. The net number of electric field lines passing through a Gaussian surface is proportional to the charge enclosed within the surface. That's it. Epsilon naught is the proportionality constant between electric flux and enclosed charge, right? So we saw enclosed mass before. This is enclosed charge. So epsilon naught phi is Q enclosed. The way we're going to see this probably most often, really, is E dot A equals Q enclosed over epsilon naught, right? Just rearranging this equation. And so thinking about charge density, we're going to be adding up charges and taking a look at how this whole thing works, calculating electric fields and that sort of thing. Again, volume, surface, linear charge densities are right, charge per volume, charge per area, charge per length, just like with mass before, except now it's electric charge. And so here's Gauss's law. Again, phi is E dot A, but we might have surfaces where you have to add up tiny little pieces of the area, right? And so, and see this line or this circle around the integral? That means it's a surface integral. We're taking the integral over a whole surface or over a loop. It's some closed area or closed line over which we're taking the integral. And but we're going to make this easy, right? We're choosing objects that have a high degree of symmetry for our Gaussian surfaces. And so E dot A, so E dA cosine theta is Q enclosed over epsilon naught, right? Phi is Q enclosed over epsilon naught. And again, E is this 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. Okay. Again, here's what all these things mean, right? Again, Q enclosed, the charge enclosed by the Gaussian surfaces, the area, electric field, and an integral taken over a closed surface. So here we go. Let's find, using Gauss's law now, find the electric field due to a point charge. So we set this up, just write this out right away. And our Gaussian surface is going to be a sphere. So what we do is we draw a dotted line around this, and we say that this sphere is our Gaussian surface. In this case, the electric field is always parallel to dA. Right? Any place where we draw the area vector for any piece of the area, it's going to be parallel to the electric field lines coming through at that point. All right, so cosine theta is just going to be 1. And if we add up all the area vectors, the magnitudes, then we get 4 pi r squared. That is the area. And E is the electric field. Right? So we know E equals 4 pi r squared over Q enclosed equals Q enclosed over epsilon naught. And we solve for E, and we end up with this, right? Q enclosed over 4 pi epsilon naught. Rearrange it, right? If we bring the epsilon naught and the 4 pi over this way, right? This ends up being K, right? 1 over, so KQ over R squared. We have now derived the electric field due to a point charge. Finally, right? Even after we had used it previously. Okay. So now let's take a look at the electric field outside of a thin spherical shell. Our Gaussian surface, again, is going to be this circle. We're going to give that radius lowercase r. Capital R is the radius, the fixed radius of the sphere. R is going to be the variable radius of the Gaussian surface. Right. And so, again, we set this up. For R greater than R, then the shell theorem tells us that the charge can be considered at the center of the shell. Right? So big R ends up not mattering. Anyway, if mattering is a word. So therefore, it's just like a point charge, and we get the same result that we had before. Right? Okay. And then the direction of the electric field depends on the sign of Q enclosed, if it's positive or negative. Outside a spherical conductor, okay, same thing. Because it's due to the shell theorem, it is just like a point charge. It's just like the electric field outside a thin spherical shell, and so we end up with the same result. Right. Okay, now finding the electric field inside of a thin spherical shell of uniform charge Q and capital R radius R. So now we're inside. So for R, little r less than big R, in this case, Q enclosed is 0. Right? So therefore, that means that the electric field is 0. That's it. And what about inside a spherical conductor? Well, if it's a spherical conductor, again, all of the charge goes to the outside. And so it's like a shell in terms of its charge. Okay. So we get to, again, electric field is just 0 anywhere inside of this spherical conductor, solid spherical conductor. Okay, outside a spherical insulator, so even if it's an insulator, it doesn't matter. All the charge is enclosed is inside. According to the shell theorem, we treat it like a point charge, same as before. And so we end up with the same result we had before, KQ over R squared. All right, and the direction, again, depends on the sign of Q enclosed. Okay, now this one is a little bit more complicated. Finding the electric field inside a spherical insulator, uniform charge Q and radius capital R. Okay, so now we have to consider the amount of charge that's enclosed within the Gaussian surface, and that's going to be changing because it's an insulator, so it's implied that the charge is distributed throughout the inside of this insulator. So we need to look at volume charge density. Rho is Q over V sphere. Q is the total charge, V is the total volume of the sphere. So that's the total charge over 4/3 pi r cubed. And then rho, as far as the Gaussian surface is concerned, is Q enclosed over V of the Gaussian surface. The Gaussian surface, again, is this dotted line that we've drawn. It is also a sphere. And so little q enclosed over 4/3 pi little r cubed. Right, so here's rho for, and these should be the same. And so we can set these equal to each other. We can use them proportionally. So then Q enclosed, we solve this, right, is rho 4/3 pi r cubed, but rho is also equal to this, so we plug this in for rho, and we get some things canceling out. We end up with Q r cubed, little r cubed, over big R cubed. Okay, so that's Q enclosed. We did all that work just to find Q enclosed, and that's going to be the general pattern here, is that we have to use this volume charge density, surface charge density, something like that to find Q enclosed in the first place. Now we can use this, and this whole thing is equal to this, right? And so E dot A, again, cosine of theta is 1 because the electric field lines are going to be pointing outward, same direction as the area vector on the surface of the sphere. And so EA, A then is just 4 pi r cubed, Q enclosed over epsilon naught. But now I plug in my stuff for Q enclosed. I solve for E, plug in Q enclosed here, simplify some things down, right? So r cubed, r squared, those cancel out. Q, and so what we end up with is this, E equals KQR over big R cubed. That looks exactly the same as the gravitational field inside of a solid spherical planet, or something like that. Okay, and the direction of the E field, again, depends on the sign of Q enclosed. And here is the graph for being inside of for the electric field due to a spherical insulator. Inside looks like this, right? KQR over big R cubed. And then outside of the radius, the fixed radius of the object, it looks like this, KQ over R squared. Looks remarkably like gravity. The main difference now is that this can also be inverted. It could be negative if this is a negatively charged object. And that's it.